We've seen how to calculate the pH of a strong acid. If you put a mole of a strong acid into water, you get a mole of hydronium. But if you put a mole of a weak acid into water, you get less than a mole of hydronium. How much depends on the value of Ka. It is possible to calculate that, but we'll save that for the next course. But what we will do here is to rank different solutions in pH. We'll see here how the concentration and the strength of an acid or a base affects the pH. We need to start our discussion by realizing that the simple fact of whether a solution is an acid or a base can help us in ranking solutions in pH. We know that solutions that contain acids should have a pH of less than 7. Solutions that contain bases should have a pH of greater than 7. Solutions that contain neither an acid nor a base would be neutral with a pH of around 7. So our first task will always be to identify the type of solution we have, acidic, basic, or neither. Remember that the acid-base chart can help. In this question, we are asked to rank 0.1 molar solutions of potassium nitrate, sodium sulfite, and carbonic acid in pH. Which has the lowest pH and which has the highest? Let's start with potassium nitrate. Hopefully by now, we can recognize this as an ionic compound, with potassium ions and nitrate ions. We know that potassium will be a spectator ion, and we do not expect it to affect the pH. In reality, ions like potassium and sodium might affect the pH by a fraction of a pH unit, but for our purposes in Chemistry 101, they do not. What about nitrate? It cannot be an acid, but what about a base, since it has a negative charge? Here is where we need to consult the acid-base chart to check on its strength. We can find nitrate on the base side of the chart, but notice that it is above the thick line near the top of the chart. All of those bases are even weaker than water. We said that they are non-basic. For the purposes of this question, that means for us that nitrate does not affect the pH of an aqueous solution to any appreciable extent. Our prediction for this solution is neutral, with a pH of around 7. Next is sodium sulfite. When it dissolves in water, we have sodium ions and sulfite ions. Sodium is again a spectator ion. We look on the acid-base chart for sulfite and we find it about halfway down. We're reminded that bases in this part of the chart are weak bases. Since we have a solution that has a spectator and a weak base in it, we expect it to be basic. Finally, H2CO3. When it dissolves, we get H2CO3 molecules. We believe this to be an acid. The acid-base chart confirms that this is not only an acid, but it is in the section of the chart where we find weak acids. Being a weak acid, this solution should be acidic. We then reason that the sodium sulfite solution should have the highest pH and carbonic acid should have the lowest pH. Simply deciding what kind of compound we have, an acid or a base, helps us locate where in the pH range the solution should be. Concentration can affect the pH as well. We want to rank in pH 0.1 molar HCl and 0.2 molar HCl. We first decide whether these are acids or bases. Of course, we recognize this as hydrochloric acid, but the H in front of the formula tells us this molecule is acidic. The second solution is more concentrated, and therefore is more acidic. Solutions that are more acidic should have a lower pH, so the 0.2 molar solution is lower in pH. What if we're asked to rank 0.1 molar sodium sulfide and 0.2 molar sodium sulfide? We first need to determine if they're acidic or basic. We see no hydrogens in the formula, and we recognize that we have a spectator, sodium, and the S2- anion, which, due to its negative charge, can act as a base. The second solution is more concentrated, so we would consider it more basic. A more basic solution would have a higher pH. Notice in each case, the more concentrated solution has a pH more towards the extremes of the pH range. Next, we have two solutions of the same concentration, but different materials. We should recognize both of them as acids since they both have the hydrogen at the front of the formula. They are both acidic, both the same concentration, but here's where the strength of the acids can play a role. We first find HCl near the top of the chart, while HF is closer to the middle of the column. HCl is a strong acid, whereas HF is a weak acid. This, of course, affects the amount of hydronium the two acids can form, and thus the pH. According to the chart, HCl is the stronger acid, so that solution will be more acidic, and therefore at a lower pH. Next, we have a comparison of 0.5 molar NaF and 0.5 molar Na2S. They're both bases and at the same concentration, but again, strength can play a role here. We find the fluoride ion and the sulfide ion in this section of the chart for weak bases. But we're reminded that bases get weaker as you go up the chart, so sulfide is the stronger of the two bases. Since sulfide is the stronger base, we can think of that solution as being more basic, and a more basic solution will have a higher pH. So, as a reminder, the type of compound, its concentration, and its strength can all play a role in the pH. Acids will have pHs less than 7, while bases will be above pH 7. As acids get more concentrated, the pH goes down. As bases get more concentrated, the pH goes up. As acids get stronger, the pH goes down. As bases get stronger, the pH goes up. A simple rule of thumb is that as solutions get more extreme, either more concentrated or stronger, the pH gets more extreme, going towards the ends of the range.